So what I'm going to do, I'm just going to sort of very quickly talk about what do we mean by corporate amnesia and why does it happen. Then I'm going to come up with a few examples that I've seen myself in my sort of day-to-day work around corporate amnesia, and then I'll just finish up with some thoughts about what we might be able to do to prevent corporate amnesia, because it's pretty costly to the construction sector. So, where do we all go for our information these days? Wikipedia, of course. It's always correct, as long as you validate it multiple ways. I quite like this definition, though. Corporate amnesia is a phrase used to describe a situation in which business and other types of cooperative organisation lose their memory of how to do things. So that this implies that at one stage we knew how to do it, but then with the passage of time, either whole organisations or bits of our organisation just fail to learn from other bits of the organisation, and we don't do quite so well. When I was putting this together, I obviously kind of just tried to sort of scratch my head myself to try and think, why does this happen? Why do we get things right and then years later we don't get them right anymore? What happens? And I'm sure this is not a comprehensive list, but these were some things that I recognised probably in my own organisation and sort of day-to-day activities. So first of all, a lot of our information is tacit. It sticks in people's heads. And it's obviously quite difficult to download the contents of somebody's brain onto paper or onto intranet sites. But often there's probably more we could do there. So because so much information resides in people's heads, when we've got a need to call upon that expertise, often people are just too busy. So you don't get the right person on the project that has the right expertise. And of course, people move around as well. Ever increasingly, people move from one organisation to another, ever increasing rates. And so we constantly have an outflux of good information leaving our organisations. Of course, you'd hope some good stuff comes in the other direction as well, which I'm sure it does, but we lose information with that movement. I see less of it these days, but if I kind of looked at my own organisation, probably sort of 10 years or so, there were quite a lot of examples where people just deliberately didn't share their information. They wanted to hold on to it because they kind of saw it as their pension. This is why you carry on employing me. Knowledge is power. And I think we see a lot less of that these days, but there's still a pitfall there. And then sometimes we have the information within our organisations, but we just don't know it's there. We don't know we've got that expertise. We don't know somebody's learned from a mistake in the past. I think then there's some more sort of cultural ones. So often, something goes wrong on a project, and it's usually a collective effort to get something wrong. It's a team effort. And there tends to be a bit of denial sometimes. So we think, well, we were involved in that, but it wasn't me that actually made this happen. And if I do it again the same way next time, everybody else will do better. And then the problem won't happen. But it never does. We get the same problem again. And then I think, often we what I call pushing the envelope. We try something in design and it works. And then when we just push it a little bit further and it works. And then we push it a little bit further and it doesn't work anymore. And so we all take a step back and we draw a red line and we publish some guidance or something in industry, and everyone follows that guidance for a number of years. And then somebody forgets why that red line was drawn in the first place. And think, well, we never get a problem here. So let's just like push it a bit further. And what happens? You get exactly the same problem that we've had in the past. And I've got a few examples of that. And then we sometimes have lack of continuity of projects. So, for example, in the UK, we've not been doing much precast segmental construction over the years because of some failures and some bans. So that kind of expertise has just sort of disappeared slightly. And when we get new projects coming back in, we've got to relearn, just due to the passage of time. And then finally, it's maybe not so much corporates, but kind of industry. I think, it's great we're having this event today because things happen, but usually it's so difficult to talk about them. Because if you start talking about it from personal experience, there's often some suggestion that you might have played a part in it. And so people tend to keep things relatively quiet. And I think it's not healthy, and anything we can do to try and get information out, like we're doing today, is obviously very helpful. I'm going to come on to some examples in a minute, but I quite like this. I'm sure everybody's familiar with this set of quotes from Donald Rumsfeld. Maybe the language isn't very elegant, but actually I think it's quite a good insight. And this is actually also quite useful when thinking about sort of what we do corporately. So I think the first one, there are known knowns. There are things we know that we know. In day-to-day, this is basically business as usual. We know what we're doing here. We've learnt the lessons. Great, we'll do some more of that. And then the known unknowns, things that we know we don't know, well, we don't do that. Then that's not within our business. You know, we'll stay away from that. If we've got to do that, we'll buy in the right expertise. Then we've got the unknown unknowns. So these are the problems that we are all going to stumble into because we don't know what we're doing here, or we thought we did, but we don't. And hopefully, yeah, we'll pick up the pieces. Nothing too serious will happen, and we'll move on from that. But for me, there was a part of this quote missing. And I'm very pleased to be able to unveil the rest of this quote. And it really was provided courtesy of Stuart Matthews, who's sitting at the front here, who retired from BRE, who's an honorary member of fibUK. And Stuart basically said there's something missing here, and that is the unknown knowns. And the unknown knowns are basically, these are the things that we do not know that we do know within our organisation, or didn't know. And that really is corporate amnesia. So I've got a few examples here, really, of things that just seem to happen repeatedly, and often repeatedly from one organisation to another, but often repeatedly within an organisation as well. And a lot of these ones, to begin with, are going to be around just curved prestressing tendons. I've seen so many issues with these in my 27 years of employment, and I can't believe it, they still happen, but they do. They're happening sort of like all around the world on a sort of pretty weekly basis, I think. So if we have a curved prestressing tendon like the one shown, you know, on the screen there, fairly obviously, you know, that generates a force into the centre of the curve. And if that tendon is too close to the cover zone, and there isn't enough strength in the cover zone, we may well see an appearance of the tendon through that cover zone. But these forces can also lead to sort of distortion of cross sections, other forces that we need to consider, but sometimes, occasionally, they do get forgotten about. Now, tendons can be curved, you know, in bridges for all sorts of reasons, and often it's just by virtue of the shape of the cross section. So, if we have a bridge like this one, and by the way, there weren't any problems with this bridge, which is why I haven't tried to crop it or not show what it is. This is built in cantilever, so you know the construction starts at each pier. The bridge meets in the middle, and then we have some pre-stressing tendons to join it up, and they often follow the shape of the soffit of the section. So in this particular situation, you'll have a downward force on the soffit there, and if we look at a cross section, this is fairly typical in a bridge. We'd have the tendons running in the middle of the slab here. That exerts a downward force. It will give rise to some bending moments and shear forces in the cross section, but there's also the potential for some local spalling. But the curvature could also be in plan as well. So this is an extract from the Docklands Light Railway extension that was early 90s. It was one of my earliest designs. And the very heavy curvature in plan in combination with the tendons running in the webs means that there's, again, an outward force from the tendons into the centre of the curve. Now, there's not a lot. I think a lot of designers will recognise that there is a force here and a problem. But amazingly, really, for me, there isn't a lot of guidance actually given in the codes on how to specifically actually design for it. And the only one I'm really aware of is the American code AASHTO, which is the American Association of State and Highway Transportation Officials. And that specifically tells you that if you've got a group of tendons like this, then you need to check the cover for the effect of local bending from that load and for shear. And if that doesn't work, then you need to put in some sort of links to confine the concrete or the tendons, or just change the designs. And this is a real issue. I couldn't find a failure photograph of this from very recently, because people tend not to want to put them on the internet. This was a very grainy old one from a paper which I'll mention a bit more detail in a minute. But this was a bridge in the US. It was a curved box girder, curved in plan, and you can see that after stressing of about 2/3 of the tendons, there was a massive great bang, and the tendons pulled out sideways through the web under that force. And what we now have is a straight length of tendon as a cord between the diaphragms at each pier. So I'm pretty sure that the designer of that never did this again. I'm pretty sure they were very, very switched on to that effect in the future. But whether they managed to communicate it to everybody else in their organisation downstream, we'll never know. There's a sort of secondary issue here, which is perhaps less appreciated, which I think, if we've got a curvature in this direction, it's very clear there's a downward force. But there's also a force of a lesser magnitude, about a third, in the transverse direction. And that's because the strands in pre-stressing are not a rigid bunch. They're not all kind of welded together. And so when they pull down, they expand out sideways. It's a bit like the pressure in a fluid, in actual fact. And if you put them, again, a high curvature too close to the edge cover zone, you will get a spalling. And again, in the old British codes, we used to not actually have to think about this in any particular detail. There was just tables. And not expecting to read this table, but this table is showing on one axis radius of curvature, on the other axis essentially pre-stressing force, and then the table is telling you how much cover to provide to prevent that bursting. And again, sort of slightly strangely, there's nothing actually in the Eurocode, for example, now that explicitly covers that problem or prompts designers to remind them to actually look at this issue. But all the things I've talked about so far, I'm going to sort of continue talking about. They've obviously been known a very, very long time. And this paper in the PCI journal it was published in 1985, and it covers pretty much all of these tendon problems as a collective around what they found around the US and Europe. And I'm not sure I can read it myself actually on the screen now, but I quite like the introduction here, which was basically saying, in the premise that those who ignore history will be condemned to relive it, this paper basically describes a whole load of failures for your delectation sort of moving forward. Now, I think I say most designers know that there's a force involved here from the tendons, but what does seem to be forgotten from time to time, and this seems to be when we actually get failures, is yes, it's very easy on a drawing to have something with a curve on it and calculate a force. But what isn't done quite so often is considerations of what if that curve is not perfectly achieved in the design, because it doesn't have to be even within the specification. There are tolerances, and the cable doesn't have to be exactly where it should be. But how often do designers actually take those additional tolerances into consideration when they calculate the forces? And sometimes you might be quite shocked if you actually do that, if you actually calculate what could legitimately be constructed and see how that changes your forces. It's quite an eye-opener sometimes. But also, I think there's some examples where I think sometimes people building these things get a bit complacent because nothing's happened on my last 3, 4, 5, 6, 7 jobs. So perhaps I don't need to be quite as careful as we have been in the past. And sometimes I think that the whole need to achieve a smooth profile isn't necessarily communicated quite as clearly perhaps as it should be. So I think certainly in the spirit of designing out risks, if you find that a design is quite sensitive to the placing of tendons, then really we need to rethink about the geometry or perhaps think about building in some links to constrain. So this is, I've tried to completely anonymise this because I don't really want people knowing which bridges are being talked about, because most of these are actually still very, very current and still kind of under a bit of discussion. So this is a typical box girder. It's not the actual construction I'm talking about, but fundamentally in the next photograph is a bridge with tendons in this sort of location, as we mentioned earlier on. The diagram up here is just indicating sort of segmental construction. So the bridge was built segment by segment. And these blue lines are the pre-stressing tendons, and the little blue lines moving up are where the tendons come out of a slab and into an anchorage blister. So it's a fairly standard sort of bridge construction. And the continuity tendons at the bottom here were being stressed up on this particular bridge not very long ago. And there was a nice sort of big cracking noise again. And then on the underside of the soffit, this large, I call it a crack, but it is a 120 mil step here, so not so much a crack as a local shear failure of the cover zone, appeared. And this line was basically following the line of one of the tendons. Upon investigation, which was sort of done through ground penetrating radar, but all the concrete was taken off so you could actually see it later on. What actually happened was that the tendons sort of going through each segment were correct in position at each joint, because there was a stop end at each joint, so they had to be in position. But under the concreting operation, which had driven the concrete down the webs of the box and into the slab, the tendons had been pushed downwards and also pushed laterally at the same time. And this was really fairly and squarely due to not supporting the tendon at sufficient intervals to give it the stiffness to stop it from doing that. If I go back to that paper from 1985, you actually see exact pictures of this scenario and exactly what will happen if you allow that to happen. So, I guess in this particular situation, not a great triumph of learning from the past. But I think, in this case, there were another set of mitigations that could have been done. So clearly, there should have been more supports to the tendons. I mean, that's just, I think, a fact. But I mean, one of the other things was that the detail employed for this particular cantilever had the tendons as a constant offset off the bottom of the section, which might sound like quite a good idea to maximise the lever arm. But on the basis that you really probably want the maximum lever arm mostly in the middle of the section, one trick which a lot of people use is to actually offset the tendon from the top of the section here, and then that both flattens out the curve, reducing the force, but it also, over most of the span, gives a greater depth of concrete to actually resist those pull-out forces. So if you do need to put in some links, locally to control that spawning effect, you only need to put them in the central area where you've got the least cover. When the cover was knocked off, then you can kind of clearly see that the tendons are displaced. You can just about see the shadow of where they were when they were first cast, where they moved to. At this stage, the tendons should be parallel, so you can see they have actually kind of moved together as well. And what I should say is none of the things I've shown, nobody was hurt, nobody was killed, so nothing like as unpleasant as the first two talks, but this is still pretty expensive to put this right. And the repair in this particular situation was to completely demolish the slab in this area right full depth after de-stressing the tendons, recast. Some additional links were put in, even though by calculation they weren't necessary, but just because they didn't want to see these tendons again. And re-stressed, and jobs are good, and on we move. This is a similar example. Now, this is some time ago. The last one was very current. This was a few years back. But it's a similar story. Balanced cantilever bridge, tendons being stressed. They're inside this section of the curve. Again, stressing, bang. This time, strangely, the people doing the stressing could see the crack because it was on the inside of the section. And you think, well, that's quite an achievement, isn't it, really, to fight the direction of curvature and have something appear on the inside. So initially the contractor said, well, this is bad design. This is a compression failure, which clearly it can't be, because if it was a compression failure, the whole flange would have disappeared with a crack in it like that. But this was another, I would say, a frequently made mistake, which is, in the design, the assumption was that the soffit would be a continuous, smooth curve. But of course, nothing actually gets built like that in segmental construction. You make a smooth curve out of a series of steps. So the design was showing a kind of constant offset off the top, when actually, to fit a constant smooth curve through a sort of threepenny bit type shape, you wanted a slight variable offset. But it was, one could say it was obvious, but it wasn't really explicitly sort of stated. And so what actually happened in the construction in the middle was a constant offset was kind of achieved in the slab. And then really, when you start to build the next segment, you realise you're pointing in the wrong direction. So a reverse curve was sort of introduced to kind of correct, to get back where they should be in the next section. And of course, this upward force here, which I haven't shown very well, it had a much smaller cover distance here than this soffit zone. And so it pulled off the top. Now, in this particular case, I mean, the extent of the damage was quite a lot smaller because of the very, very localised damage, but it was still a blooming nuisance, delayed the programme. And in this case, the solution was fairly similar. So the tendons were de-stressed, the concrete was removed, then the tendons were lightly stressed just to take out any bend in it, straighten it up a bit, and then de-stressed and then reconcreted. But in both of these situations, the interesting thing is it was not somebody being unaware of the problem. It was experienced designers and experienced contractors. And they'd heard about these sorts of problems, but it never happened to them before. And in many ways, I think it's difficult to kind of rule out a degree of complacency, actually, in some of this design, and not communicating risks maybe as well as should have been. Um, Again, people that have designed sort of pre-stressed concrete bridges are generally aware of the pitfalls of these anchorage blisters. So this is where these sorts of tendons we've been talking about get anchored off inside a box. And there's very, very high curvature out of necessity in these regions here. And so in design, you know, the assumption is that this nice smooth curve will be taken by all these links which are nicely confined within this anchor block. But it is incredibly difficult, given the sort of congestion of steel, to always achieve a perfect curve. So sometimes, you know, there's a danger that this will happen and that all of that curvature will get concentrated into a nasty kink. And if that nasty kink is actually not itself within the blister, you know, then you can get problems with a sort of little pop-out failures here. This is remarkably common. And you can see an example of it here. So that I think we must have either a deliberate steel curvature in this zone or a pop-out or a kink that's caused a local spawning of the concrete here. And I think, you know, to avoid this sorts of thing, then, you know, in design, you really want to keep the end of that curvature, the tangent point here, well inside this blister, and communicate the pitfalls of what might happen if you don't do that. And again, here you can see another example of where, again, I don't know whether this is because the design actually had still some curvature going into the slab, or whether this was not constructed properly. But again, you've obviously got curvature going on outside here that's led to this sort of spool. Deviators, so this is an external post-tensioned construction. So often we have tendons inside a box that get a very sharp change in angle at a specific feature, like a deviator here. And of course, the deviator's role is to transfer that big shear force into the webs. There's no way that's going to fail. But what you can get is if the cables themselves get kinked at the face here and press on the cover zone of the concrete, then you can get local failures there, which then again just slow you down and require some treatment. There's at least three ways of preventing this. One is to put some compressible material into the cover zone that actually will ensure that any concentrated forces can't bear on the cover zone and bear more inside. There are bell mouth details where the pipes inside here have a flare on the outside that stop contact. And there's what I call the overbent solution here, where instead of having a radius over the full width here, you choose to keep your tangent points some way inside. So the radius becomes tighter. But by doing that, we have some tolerance. So if the cables are not quite aligned in the way they should be, you just move the tangent point around the curve, and with deflections, the tangent point removes from around the curve, but we keep the force away from the cover zone. And I think, you know, these solutions are quite well known, but all the projects I've been involved with, there's always some pressure at some point comes through the contractor to say, well, I don't want to do a bell mouth, that's expensive. I don't want to put in compressible material, that's a bloody nuisance. I don't really believe in this overbent pipe solution. And I think certainly if you do nothing at all, then yeah, this is pretty usually the outcome. And you can see here that we've got pretty much a kink force occurring at the cover zone here. And I know this organisation, has designed these before and not had problems. You know, so something's gone wrong in either being under pressure or not having learned from a previous team. And I think, you know, when these things happen, you know, these are some of the sort of phrases that kind of come out, you know, from people. So, you know, didn't know it was a problem. That's probably not so much the case. This one's more the case. You know, we've detailed this. We've detailed this before, but you know, we've always been criticised for over detailing. You know, and so we kind of slackened things off a little bit this time. And oh dear, look what happened. Congestion's often the problem. Trying to fit things into sort of very congested areas generates big curves, which makes it difficult to construct. But I think number one is often construction program pressures as well, particularly with setting out. So just a couple of things just to finish with. I'm very conscious of time. Much smaller things. I was talking to Akram earlier on, and I think you said something like, this is the bane of my life or something. But so many times I've seen drawings like this with fairly small piles often, and a perfectly drawn grid of bars, and nicely placed bars in a circle, and then some sort of note to say, you know, adjust them on site. Which is all very well and good until you come to site and that's the view that you've got, which is quite a challenge. And Yeah, you might, if you're lucky, you might get one of the main bars through the middle of it. You might then choose to stick in some smaller ones in a gap, which probably don't go all the way through, and then the main bars go on the outside, and that's the best you can do. I certainly had a fair share of problems in Atkins with these. So particularly for smaller sort of piles where this is a permanent problem, we just came up with a different detail where we basically were saying put most of your main reinforcement outside the pile. That means you can have a distribution from the pile out to these bars. You've got to put in some distribution steel in the other direction, and you have to make the pile cap a little bit bigger as well to fit those in. But if you do that, you won't get this congestion problem. And we've had, I would say, 100% success. We've employed that detail. But every now and then, there's always one team that value engineers it back in the other direction again. So the pile cap's a bit bigger than it needs to be. Let's make it a bit smaller, and then what you get corporate amnesia, and this was a fairly bloody annoying recent one. Again, when we're back to square one again. Where these all have to be cropped off, and you get the email from the contractor. We're sitting around waiting. It's very expensive sitting around waiting here. What are you going to do about it? So certainly within our internal sort of guidance notes we've been putting together for many years now, as well as telling people what to do, we also give the background about why. So that people don't forget, with the course of time, but revalue engineer, in inverted commas, back in the other direction. I put this one in as well because I think this is another sort of quite good example of very effective industry guidance that actually stops a problem, but then people run the risk of forgetting why that guidance was there and then overstepping the mark again. And this is the problems with hydrogen embrittlement with bolts. I won't go into this in any detail, but for hydrogen embrittlement to occur, you need three basic things. You've got to have hydrogen there, which might come as part of the electroplating process of the bolts, or it might come from just corrosion in service. You've got to have a relatively high percentage of stress, typically more than 50% of the capacity of the steel, and then you've got to have susceptibility of the steel, and basically that is a high tensile grade of bolt. So an 8.8, no risk. 12.9 bolt, great risk. A 10.9 bolt, opinion is divided on this, but current guidance is erring on the sort of side of caution. And I say there's plenty of guidance out there. I mean, the pretty much all guidance in kind of civil engineering says not to use these sort of bolts outside or with electroplating. For 10.9 bolts, basically don't galvanise with acid pickling because that introduces hydrogen, and don't use electroplating. And if you are using 10.9 bolts, try not to use them in heavily corrosive environments, because if they do corrode, you might get this effect. Sorry. But again, I think this is where sort of periodically people forget why those lines are there. I've had to crop out most of this. This was a gantry that fell over fairly recently. You can just see the upturned sort of base plate there. And this was a classic case of this was originally designed to using grade 8.8 bolts. Following the guidance, essentially. The contractor didn't have any 8.8 bolts in that particular diameter, but he did have some 12.9 in a smaller diameter that provided the same capacity. So they were put in, and 18 months later, a bit of corrosion had occurred, and hydrogen embrittlement set in, and one of the bolts failed, and then the others all failed as well at the same time. So a pretty cautionary mistake, and that particular team involved, I'm sure, won't make that mistake again. Let me just jump over that. So just literally just to conclude, just one thing that we've done kind of internally within Atkins to try and help with this, with I'd say some success. Going back about 10 years ago, I think we realised we just had too many areas where we were not learning properly from one office to another, and that's still corporate amnesia, because everybody else that looks at Atkins sees Atkins. They don't see the Atkins Croydon office, or so we realised that we had very, very effective technical networks that were able to talk to each other and ask each other questions, but we hadn't been very good at actually physically writing stuff down and then making sure we brought that back into our design practice. So we brought in a formal lessons learned process about 10 years ago. We wrote up about it. I can't remember the date of this. It's probably about 2011, in the IC proceedings about it. And very, very simply, and I'll, by the way, not for a minute trying to suggest this is like everyone should go away and do this if they haven't got one, because it just kind of works for us. We've just set a very, very simple lessons learned register, which everyone is obliged to use on a project if they do something good, or if they do something not so good that they don't want others to repeat. You put in your project, you put in a bit about what was good about it, what wasn't so good about it. We use our technical networks to assign it to the professional head of that network, and it's then their responsibility to do something with that information. Whatever it is, it might be to write a technical instruction, a guidance note, change our software or whatever, but it's their job to do that. We don't require too much information, because that's the key. If you ask lots of information from somebody, they won't put anything in. So we require the bare minimum, just like what was it you did and what happened, good or bad. The professional head, poor chap, has to go and, or woman has to go and follow up and do something with it. This then becomes really our source of ongoing guidance notes and instructions. I mean, a typical example here was something around precast deck panels. Somebody on a job came out with a new improved detail. It saved the contractor a lot of money, so we've written it up, and that's now our standard way of doing full depth precast deck panels. The output is usually, as I say, some sort of guidance note. And critically, if it was a bad thing we've got to avoid, it tells you what it was, but it also gives you the background about why to avoid it, so we don't forget the learning from that. Of course, it doesn't oblige anybody to pick up the blasted thing when you've written it. They can still ignore it, which is a challenge. And so, what we've done on top of that is people working in sort of Bridges world for big customers like Highways England or Network Rail know that the clients have a technical approval list of all the standards that you've got to follow. And internally, we have exactly the same for our guidance notes. So we list them, we have them all listed out. Designers have to go through and tick which ones actually apply on their projects. Still doesn't solve it every time, because not everybody complies with our processes, of course, but it has helped a great deal. And I guess that's all I can kind of say really on that one. So just to sum up, I think there's all sorts of things going on in the industry at the moment to try and improve our productivity and make things better. But I think if we could just cut out some of these frequently repeated mistakes, we'd probably be a lot better off. A formal lessons learned process has worked very well for us, but we're far from perfect. And beware the unknown knowns, courtesy of Stuart Matthews. Thank you very much, Stuart, and thank you, everybody.